So here in section 9.3, we are going to compare two populations, but with a paired difference experiment. So these are commonly used with before and after experiments where you have multiple measurements on the same individual here. Your observations are dependent because they're related to the individual who's measured. The idea here is we'll compute differences of our pairs and then just do a one sample test on the differences. So the kind of problem that we would tackle here would be, for example, a researcher randomly selects 10 individuals and tests their grip strength in their dominant hand versus non-dominant hand. Results are here in the table, and they want to use a hypothesis test to determine if the population is stronger in their dominant hand at the 0.05 level. So what we would do is we would just calculate the differences there and try to show that the difference was positive if you're doing dominant versus non-dominant. Now, in order to do this type of a test, we need our sampling distribution for the differences here to be approximately normal. So here's the test requirements when you do a paired difference. You need random sample. The sample data need to be matched pairs. So up here, we had dominant and non-dominant for the same individual. So that's a matched pair because they both relate to that same individual. So each line here is a matched pair. The differences here need to be normally distributed, and the sample size is at most 5% of the population. So if that's the case, then we calculate the mean of the differences, denoted x bar sub d, the standard deviation of the differences, denoted s sub d, and then d0 is going to be our hypothesized difference, usually 0. And then if we have a large sample, our test statistic will be the mean of the differences minus d0 divided by sigma over root n. Use S over root n if you don't know sigma. For a small sample, you'll use a t-test here, x bar sub d minus d0 over s sub d over root n. Degrees of freedom will be number of differences minus 1. So you will reject your null hypothesis if the t or z is past the critical value. Or if p is less than alpha, then you would reject your null hypothesis. So let's take a look at this example here and see how we would test here. So for our differences, we're going to do dominant minus non-dominant. So dominant minus the non. So subtract left minus right. 28 minus 25, 3. 3, negative 1, 3, 4, negative 6, 1, 0, 2, and negative 1. So then we need those differences to be approximately normal. So if we start checking our conditions here, random sample, yes. The data are matched pairs. Differences are normally distributed. So I did a normality assessment with our spreadsheet. So I entered in our differences right here. I clicked go. We got nearly normal true and okay for t-test. And we will have to use a t-test because sample size is less than 30. Now the Pearson test did come up as a false, but this is not too bad. I mean, if you look down here at the normality plot, we see that most of the data is in a nice straight line, but we do have that one outlier there, outlier on the normality plot. So, but most of the data, nice straight line here. So on the basis of 2 out of 3 tests, we'll go ahead and say that this is approximately normal. So it's approximately normal. We do have, does look like we have one outlier. So this is not quite satisfied. So that would be, that would call our results into question if they're close. Sample size is at most 5% of the population. That is also satisfied. So let's go ahead and carry out the test here. So null and alternative hypothesis. So if the dominant minus non-dominant is positive, then that would establish that the dominant is stronger. So that's saying population mean of differences greater than 0. If that's not the case, the mean of the differences will be equal 0. Level of significance, step 2, that was given as 0.05. Sketch the rejection region of the distribution. So this is a greater than test, so our rejection region will be on the right-hand side. So I have one rejection region. And this critical value here is going to be a t-value. It's the t-value with 0.05 to the right. So t.05 is going to be equal to inverse t. The left area over here is 0.95. And then degrees of freedom, there are 10 differences. Minus 1 is 9. So if we key that into the calculator here, go to the distribution menu, and we want inverse t, number 4. Our area 0.95, degrees of freedom 9, 1.83. So there's our critical value. Now we need to compute the test statistic. We need the mean and standard deviation of the differences. So I did one variable stats here, and I got the mean of the differences to be 0.8 and the standard deviation of the differences to be 2.97. So again, all I did there was I went to stat edit, did a list, entered in my differences here, and then I went to stat, calc, and one variable stats. And there's my x bar and my standard deviation. So then our x bar there is 0.8. D0 is equal to 0. So 0.8 on the top. 2.97 is our standard deviation. Divide by square root of 10. And if you enter this into the calculator, you will get 0.85. So that's our test statistic. So 0.85 would be about right here. So t-test is 0.85. And we see that's not in the rejection region here. So t-test is 0.85. which is less than 1.83, and so we do not reject. So that's step 5. Step 6, state our conclusion. So we do not reject, so that means that there is not sufficient evidence to conclude the alternative hypothesis, mean of differences is greater than 0. So we're going to conclude that the mean of differences equals 0. So that means that the dominant hand is not stronger than the non-dominant. So dominant is not stronger is practical conclusion. We can verify this with p-values here. So our p-value is the area past the test statistic. That's the 0.85. So this will be probability that t is greater than 0.85. So we'll do that with TCDF. Right, here's our calculation for our test statistic 85065. So we can do 0.85065. We'll put in the extra decimals here. Is our lower cutoff. Upper cutoff is infinity. We'll use 10,000. And degrees of freedom are 9. So if we enter that into the calculator, so second variables, go to that distribution menu. TCDF number 6. And we want, let's see, this will be 0.85065. Upper 10,000. Degrees of freedom 9. 2085. And we notice here that our P, which is 0.2085, is greater than 0.05, which is alpha. So again, we do not reject H0. So we get the same conclusion both ways. And then if you want to verify this with the calculator functions, we can go to stat, tests, and then we just do a t-test, one variable. So we've actually got data that we input, and our hypothesized mean here was 0, the null hypothesis mean, 0.8, 2.97, and n equals 10. And that's all data that's being put in from our, that's summary stats. We want data. We've actually got data here. So we want enter there. Hypothesized mean 0, we're using list 1. And then our alternative hypothesis is a greater than. So highlight greater. Come down and calculate. And there's our test statistic, our p-value 2085, and mean and standard deviation. So that's confirming what we did by hand.